Hey everyone. So in this session, we're going to go into a little bit more detail about the dynamics of the expansion of the universe, how that expansion rate can change, and how this is going to tell us something about the composition of the universe. So in earlier sessions, we've talked about Einstein's theory of relativity, saying that matter and energy can warp the geometry of space-time, and specifically that this geometry can expand. And this is what we talk about for the Big Bang and the expanding universe, that the geometry of space and time itself is actually changing. We've also talked about the cosmological principle that the universe is, on large scales, homogeneous, there's no special locations, and isotropic, that there's no special directions. And for the large scale geometry of the universe, there are only a few kinds of geometry that actually satisfy this cosmological principle that there's no special directions, no special locations. We can have what's called a positive curvature space. So think the surface of a sphere for a positive curvature. We can have this weird kind of saddle shape if the universe has a negative curvature. And if the universe has zero curvature, is perfectly flat, then that would be just a flat space extending infinitely in all directions. But at this current time, we're still not 100% sure on exactly what kind of geometry our universe has. We're going to talk about that a little bit. We also saw how the redshift of distant galaxies matches our general expectations for an expanding universe. But what we're going to talk about now is how the matter and energy content of the universe affects the dynamics of how that expansion occurs. Is that expansion rate changing? So the thing that I want to point out right now is that the matter and energy content of the universe can change. So changes how the rate of expansion changes. How the rate of expansion changes. And this is going to have important consequences for what we think the universe was like in the past. How has that expansion rate potentially changed over time to what we see today? And it also has an effect on what we think the future of the universe is going to be. How is that expansion rate changing and what might happen very, very long time scales from now? So there's going to be a little bit of math portions in this, but we're not going to focus on the math. We're going to focus more on the conceptual side, but there are going to be some math-ish looking things. So again, the idea is how the geometry of the universe changes over time depends on the mass and energy content of the universe. So let's say the universe expanded by a certain factor. We're going to call this the scale factor A. If I have a universe that is just full of matter, and let's say I double the size of the universe, imagine a cube of space containing a bunch of matter, and I double each side length. It's double the width, double the length, and double the height. Well, that matter is going to become more and more dilute. As the universe expands, all those little bits of matter are going to get further and further apart from each other. And this matter density is going to dilute by 1 over that scale factor cubed. Basically, if I double the size of that universe, well, that volume that I was looking at, the length doubles, the width doubles, the height doubles. So I've got 2 cubed times more volume. And that matter is spread out over that much larger volume. So as the universe expands, that matter energy density is going to decrease, and that's going to change how the expansion rate is affected. On the other hand, if I have a universe made up of radiation, made up of photons, what's going to happen there as the universe expands? Well, first, the photons are becoming more dilute as the universe expands, just like the matter did. Universe expands, these photons are getting further and further apart from each other. But in addition to that, for these photons, the wavelength of those photons is going to increase as well. And longer wavelength photons carry less energy. So in addition to saying those photons are losing energy density because the universe is larger and those photons are more spread out, they're also losing energy because of their redshift. Those wavelengths are increasing, and that means how their energy density changes as the universe expands, that energy density is going to drop off even faster as the universe expands. So in this expanding universe, matter and radiation are affected differently as the universe expands. And since their energy densities are going to change in different ways, there's going to be a feedback effect on how that energy density then goes back and affects the expansion rate of the universe. So a universe containing different kinds of materials is going to change in different ways. It's going to have different kinds of dynamics in how the expansion rate of the universe is actually changing. Not only does the type of radiation affect how the universe is going to evolve, but also how much matter and energy density is in the universe is going to affect how the universe has evolved in the past and will evolve in the future. If I have too much matter, so let's look at a couple of quick cases. If I have too much matter, then we're going to have that positive curvature space. So this affects the overall curvature of space. So positive curvature. And gravity wins. And gravity is going to win out, cause that expansion rate to slow down, and eventually turn around and cause the universe to recollapse. So if there's too much matter, we get this positive curvature and gravity wins. Universe recollapses. So right now we see the universe as expanding, but if our universe contains too much matter, that expansion rate will slow down, stop, and actually turn around and eventually crunch back in on each other. What if the universe has too little matter? So too little matter, matter and energy, we're going to get a negative curvature, kind of that saddle-shaped universe instead of the spherical universe. So negative curvature. And expansion rate will continue forever. It'll slow down as it gets larger and larger. If we had a completely empty universe, the expansion rate would just stay the same and the universe would keep expanding at that same rate forever. But if there's not enough matter, we get this, what we call an open universe, where the rate of expansion will slow down a little bit, but the universe will keep on expanding forever. So universe expands forever. And there's a critical point where we have a flat universe. So this point in the middle is the flat universe. And the expansion rate will slow down and always almost stop. So, and the universe expansion rate just barely doesn't stop. right? Just barely doesn't stop. I like using the analogy of throwing a ball in the air. Um, let's say I throw this ball up, but the expansion rate, and we're going to kind of model the height that the ball reaches, the movement up as being the expansion of our universe. So if I throw this just at a kind of ordinary rate and gravity is winning out, well, that expansion of the universe is going to stop, turn around, and eventually recollapse on itself. But imagine I could throw this at the Earth's escape velocity. Well, then the object's going to fly away, and if I could throw it that fast, it would never actually return to the ground. That would be like the one of these open universes where the expansion rate is high enough, gravity is weak enough that the universe just expands forever. So what we want to do is try to identify how much stuff is in the universe and how does it relate to this critical density? How close are we to that critical density for these different kinds of universes? So let's talk about the composition of the universe. Composition of the universe. We can look at ordinary stars, clouds of dust and gas in between space and in the disk of spiral galaxies, and we can try to estimate the total mass. When we look at the universe, so for ordinary matter, it's about 5% of this critical density of critical density. About 0.5% of the critical density of the universe is in stars. About 4.5% is a mixture of gas and dust clouds. Again, even though we talk about stars having a lot of mass, the majority of the ordinary matter that we see is still going to be in these gas and dust clouds. How do we identify this? Well, we can look at, again, just counting up stars and clouds of dust and gas and identify how much material seems to be there. We can also look at this graph that we saw earlier in a previous session when we were talking about the evidence for the Big Bang, saying that universes with different amounts of ordinary material would have produced different amounts of helium, deuterium, helium-3, lithium. Those amounts of those elements that we see are, again, suggestive that we are correct that this is the amount of ordinary matter that would have been in the early universe. If there would have been a lot more or a lot less, the abundances that we see of things like helium-3 and lithium-7 and deuterium, those amounts would have been affected and we would have been able to measure that. So we seem to say if we're just looking at the ordinary matter, it's much, much too low, much further below this critical density to actually get this kind of universe that expands, but just kind of gradually coasts to a gentle stop. We don't have enough mass for that if we just look at ordinary matter. But we always want to ask, are we missing anything? Can we look up any other methods of measuring the amount of mass that's in our universe? And this is going to lead us to talking about dark matter and dark energy. We're going to talk about dark matter in this session. Dark energy we're going to have in the next session. But we've talked about dark matter a little bit earlier. So for dark matter, we looked at the rotation curves of galaxies, saying if I look at the orbits of different objects, we can use a modified version of Kepler's third law to estimate how much mass is inside of that orbit. So we do this for galaxies and look at different objects orbiting at different distances around that galaxy. And we see that the rotation rates of these galaxies, especially further out, are much, much faster than we would expect just from the presence of the ordinary visible matter. So galaxy rotation rates are too high if there isn't some additional matter. Too high if only visible matter present. Those objects in those galaxies are spinning around so fast that there must be additional gravity pulling on that, the gravity from larger masses pulling on that to give it those higher orbital speeds. So those higher velocities imply that there is much more mass present there than we can see with optical telescopes. So this dark matter stuff, right now, dark matter is just a placeholder name. We do not know, as of this point, what dark matter physically consists of. We haven't been able to, as of yet, test it in the lab in a way that's been confirmed by backup experiments. We're going to talk about some of the experiments that have been tried, and there have been tentative results, but that haven't survived repeated testing. And again, this dark matter doesn't interact with light in any way. So let me put this down just as a reminder. So the dark matter doesn't seem to interact with light in any way. Doesn't interact with light in any way. It doesn't give off light. It doesn't reflect light. It doesn't even block light. If I have a big cloud of dark matter, this big mass of dark matter, and there are some stars behind it, the light from those stars is able to pass completely through that dark matter without being affected at all. It doesn't interact, the dark matter does not interact with light in any way. But we want to look at more evidence for dark matter than just these rotation rates of galaxies. So we can look at galaxies in galaxy clusters. So another line of evidence for dark matter is in galaxy clusters, individual galaxies are moving too fast based on just the presence of the visible matter. So galaxies in clusters are moving too fast. If I can spell there, sorry about that. So again, in a cluster of galaxies, they're all orbiting around each other, but these galaxies are moving much too fast based on just the gravitational influence of the visible matter that we can see, the stars and the gas and dust clouds. It's not enough mass to give these galaxies these different orbital velocities, hinting that there's some more matter. So again, this is more signs of dark matter. We can also look at gases inside of these clusters. If I have a thin gas free falling in a gravitational well, those gases, as they're compressed by gravity, as they kind of free fall in this gravitational well, those gases are going to heat up. Gravity pulls those gas particles in. Those gas particles collide and rub against other gas particles, causing them to heat up. And we can measure how much these gases are heating up. The deeper the gravitational well, the higher these temperatures, the temperature of these gases are going to reach. Well, we see galaxy clusters that contain galaxies or gas clouds that are emitting large amounts of X-rays. Those gases must be have been heated up to very, very high temperatures. And once again, we see that these gases are heating up more than they should if there were only the ordinary matter present. So gases in galaxy clusters heating too much. And again, this suggests more mass is present. Because again, the deeper, the more mass is present, the deeper that gravitational well that's going to be produced. And as those gases fall inwards, the more violently they're going to be heated up. And when we look at the actual abundances in this case, in these clusters, the estimates are that there's around 85% dark matter, 13% hot gases, and about 2% stars. So of the matter in these galaxies, of the mass, I should say, in these clusters, the dominant effect by far is about 85% dark matter, with about 13% gases and 2% stars. Again, I want to highlight that we're not off by a small amount here. We're saying that not only are we missing some mass, we're missing the vast majority of the mass in these galaxies. There is one more way of trying to detect this dark matter, at least that we've successfully been able to apply. This effect called gravitational lensing. Gravitational lensing, if I have some distant galaxy and I'm trying to receive the light from that distant galaxy, let's say there's a foreground object, say a cluster of galaxies that has a lot of mass. Well, according to Einstein's theory of gravity, that curvature of space-time, that effect of gravity is the effect of the curvature of space-time, that can actually deflect light rays. So high mass objects can deflect the path of light rays. Write this one down. So high masses can deflect the path of light. So what happens, what this looks like is, let's say there's a distant galaxy, I'm seeing its light, but there's this foreground massive object, could be a cluster of galaxies. Well, some of the light that was going from that galaxy that would have otherwise missed us, that the path of that light ray is going to be bent by the presence of these galaxies and swing it back towards us. And what we get is this distorted image, this kind of virtual image of the same galaxy, but distorted and to the side of these massive foreground objects. So if we have this cluster of galaxies containing a lot of dark matter, the more mass is present, the more we're going to get this gravitational lensing effect and see these distorted images of background galaxies. Sometimes we can see multiple images. So more mass, more distortion. So more mass, more distortion. Here are some images. Let me actually zoom in on this just to make this, just to see this a little bit clearer. These are some examples of gravitational lensing effects. You can see these foreground galaxies, and to the sides, we see all these kind of wispy little lines that seem to be curved around this cluster of galaxies. What that is we have this cluster of galaxies, and we have some light source behind it, some other galaxy behind it. And the light from that background galaxy, it's being bent around this foreground mass. It's being bent around that foreground mass and giving us these weird lensing effects. We literally call this gravitational lensing because it's like putting a lens over top of an object and getting those weird kinds of distortions. These are some more dramatic examples of we have this foreground galaxy And what we see here is a single background galaxy. And it's really, really nicely aligned so that all of that light coming from that background galaxy is making what we call an Einstein ring around this foreground galaxy. This is a single galaxy behind this one. In this image here, we actually see multiple images, multiple distorted images of the same galaxy. This blue kind of weird wispy line over here is the same galaxy as this one over here. You might ask, how do we know that's actually the same galaxy and not just a galaxy that looks like the other galaxy? Well, there have been cases where we've seen a supernova. We've seen one of these lensed galaxies, this multiple images of it, and in that background galaxy, a supernova has gone off. That supernova goes off in the background galaxy, and in both of these images, in both of these weird distorted images that we're seeing of this galaxy, we see that supernova go off at the same time, sometimes with a couple-hour delay just because how that light is bent around. One path might have been a little bit longer than the other by a couple of light hours when this light has been coming to us for billions of years. So basically the same time. It would be a staggering coincidence if similar supernovas went off in both of these galaxies at the same time. So we see them at the same time. So we can confirm that, yes, these are multiple images of the same galaxy being distorted by this gravitational lensing effect. So again, the more mass is there, the more distortions we're going to get. And we see enough distortions that this dark matter stuff seems to be present. There's more matter there than just what we can account for with visible matter. So again, just to kind of summarize, for identifying dark matter, we've got galaxies are rotating faster than they should. More mass should be present. Galaxies and clusters are orbiting around the cluster faster than they should. More mass needs to be present. The gases in those galaxy clusters are heating up more than they should because they're falling into a deeper gravitational well owing to the presence of more mass. And the amount of distortions that we see from gravitational lensing events, those are greater than we would expect just based on the visible matter. More hidden matter has to be present. So again, I hope I'm bringing apart a reasonably convincing case that something weird is going on here. And at this point, there's kind of two options available. Okay? One, there is some kind of extra mass out there, some kind of material out there, and we are seeing its gravitational effects on ordinary matter. Another option is all of these ways of detecting dark matter are based on our understanding of gravity. The galaxies are rotating too quickly if our understanding of gravity is correct. The galaxies in these clusters are moving around too quickly if our understanding of gravity is correct. The way that the gases are heating up, or these gravitational lensing effects, those are not acting in the way that they would if our understanding of gravity is correct. But maybe something is wrong with our understanding of gravity on these very, very large scales, causing us to accidentally apply our understanding of gravity in a situation where it's not quite accurate enough. And both of these options are receiving a lot of scientific interest, a lot of study. There are modified theories of gravity that are being studied, but right now, again, this could change with future observations. There's still a lot of open questions about this. I'm going to be highlighting some of those open questions now. A lot of the modified theories of gravity either don't agree with current observations, or the differences of these modified theories of gravity, at least in situations that we can directly test, like things in our own solar system or things in the lab, don't show enough of a discrepancy on these smaller scales to, as of yet, be able to distinguish these modified theories of gravity from our understanding of general relativity. And again, a lot of effort has been put into this, but a lot of effort has also been put into trying to find what is this dark matter? Can we actually see it in the lab? So again, it's still a very open question on which of these options are correct. But for now, we're going to say, let's assume that our understanding of general relativity is correct. Because again, so far, general relativity has been able to pass every single test we've been able to throw at it. So let's talk about this first option in a bit more detail. So most astronomers and physicists prefer the first option, but it would be a slim majority at this current time. So what is dark matter made of? There are two general classes of possibilities. So let's talk about dark matter composition. We've got two general classes of possibilities. One, we're going to call the machos, massive compact halo objects. These are things that are still made of ordinary matter, nothing off the periodic table, but that don't give off much light. So we have these machos, massive, compact halo objects. So things like dead stars. So things like black holes, neutron stars, if they're not accreting, they don't give off very much light. Could be rogue planets that were ejected from solar systems flying through space. Could be brown dwarfs. Again, a lot of options for those machos. Or in battle with the machos, we have the WIMPs. These are weakly interacting massive particles. So it would be something that we haven't actually measured yet, a new kind of particle. So new particle that would have the properties basically of a much more massive version of a neutrino. So neutrino-like, but more massive. So we want to try to distinguish which of these options is more or less likely. So we need some sort of observation or some sort of experiment that we can do to try to identify which of these options is more likely. Again, it could still be neither of these. It could still be that, maybe our understanding of gravity is wrong, but this is still, at least right now, the leading hypothesis, so that it's some kind of material. Well, the machos, let's look at those first. The machos, if it's these massive compact halo objects, then every once in a while, when we're looking at a distant star, every once in a while, one of these machos should pass in front of that star. And that same gravitational lensing effect, when I take that dead star core and pass it in front of the star, the light from that background star, rather than being blocked, the light from that star is going to be gravitationally focused onto us. This is referred to as a micro-lensing event, and we have seen some of these events happen. So these massive compact objects can occasionally make background stars appear a little bit brighter, but the problem is we don't see enough of these micro-lensing events. So for these machos, it's kind of unlikely that these machos are the source of dark matter because we don't see enough microlensing. And if this hidden extra mass, if this huge amount of extra mass is actually throwing things off, then earlier on, when we looked at the abundance of these primordial elements, saying how much of this was produced in the early Big Bang, if these machos were the source of dark matter, that would still be made of ordinary material, and that would have thrown off these values. So the presence of that extra matter would have changed our observations of the Big Bang nucleosynthesis. So let me write that one down real quick. So extraordinary matter would change Big Bang nucleosynthesis. Changes era of nucleosynthesis. Which, again, would be evidence against those machos. So in the battle between machos and WIMPs, actually, when I was taking similar astronomy courses in my own undergraduate career, machos were thought to be the more likely candidate. But as these surveys were being done trying to look for these microlensing events, it became clear that there's not nearly enough of these microlensing events for machos to be a significant portion of dark matter. So based on our current observations, it seems that this dark matter is some kind of new type of particle. Again, it would have to be very massive, but only interact with ordinary matter through the weak force and the gravitational force. Again, like a neutrino, but more massive. And there are different models of extension of the standard model of particle physics that provides hypothesized candidates. So there are particle physics extensions that pretty naturally lead to some of the some kinds of particles that might have these properties. So there are some hypotheses, so particle physics, involving particles like this. Unfortunately, at this current point, we haven't been able to directly detect these dark matter particles yet. Scientists are working very hard to try to detect these particles. Some experiments have proposed some data that looks like it might be an early detection, but follow-up observations haven't actually bore out those results. Remember, science is an iterative process. We propose an experiment, we try that experiment, and then we see if that experiment is repeatable. So this is, as of yet, undetected. And the fact that we haven't detected any of these so far is kind of pushing some scientists back to the drawing board of saying, wait, maybe it is gravity that is, maybe it is a problem with our understanding of gravity, or maybe there's something else going on that we haven't thought of yet. I was once asked by a student when I was going through this kind of this description, I was asked by that student, so do scientists just kind of like make stuff up and then, just make a whole bunch of guesses and see what works? And the answer to that is partially yes. We try to come up with as many ideas as we can, and then in any kind of science, we look to try to disprove each one of those ideas. So we come up with a model of, oh, maybe it's this new kind of particle. How might I be able to detect it? Maybe dark matter particles will go through decays or annihilate, and we might see the particles that are coming off from those kinds of reactions. There are experiments that are currently underway looking for those kinds of signals. And then we try to say, well, what predictions do each models make? And then we go out and try to look for the positive evidence of each of those predictions. and again, try to narrow down our ideas from that. When we look at the large-scale structure, we said that galaxies tend to clump together. Galaxies don't form in isolated spaces. They tend to form in clusters and superclusters. Well, dark matter should gravitationally clump together in a somewhat similar way. A little bit similar, a little bit different. We're not going to talk about the details of this too much, but the ordinary particles, if these dark matter particles are in fact these WIMPs, these new kinds of particles, then while ordinary matter should fall to the centers of these higher density clumps, the dark matter should stay in these larger halos around them. So when we look at simulations of the large-scale structure of the universe that include these kinds of dark matter particles, they're actually pretty good at being able to predict the large-scale structure of the universe. So we again get that idea that the dark matter stays in halos around galaxies. Let me write this down. So these particles would stay in halos around galaxies. And the dark matter that we are proposing when we look at computer simulations of the large-scale structure of the universe, models of large-scale structure of the universe that include dark matter and include the gravitational effects of dark matter seem to be much more accurate at producing large-scale structure. So simulations of the universe including dark matter, again, dark matter as these kinds of weakly interacting massive particles, these kind of massive neutrino-like things, are better at predicting large-scale structure, are better at producing large-scale structure. So overall, let's kind of talk about this as a quick summary on dark matter. While we can't detect this dark matter yet, we do see the gravitational effects of dark matter on ordinary matter. So if our understanding of gravity is correct, we can see that there is some additional mass, a lot of extra mass that seems to be kind of going around the universe. And in the same way that if I look outside and I see the leaves on a tree kind of shaking violently, I can infer that it's windy outside. Even though I can't directly see the wind, I can see its effect on things around it. In the same kind of way, we can see dark matter's gravitational effect on things around it. Dark matter most likely consists as some as yet unidentified particle, though again, as I mentioned, current surveys to detect this dark matter directly have so far not been successful or have not been repeatable. And this is leading some scientists to kind of decrease this probability at least a little bit. And models that involve dark matter do a better job at simulating the large-scale structure of galaxies and galaxy clusters. So again, this is why a lot of scientists, even though we haven't directly detected this dark matter yet, still think that dark matter is the most likely candidate for explaining these effects of the galaxies rotating too quickly, galaxies and clusters moving too fast, the gases in galaxy clusters heating up too much, and the amount of distortion we see in these gravitational lensing effects. So in the next session, we'll talk a little bit about dark energy and see what else might be in our universe and what effects it has on the evolution and the expansion rate in the universe.